Hi guys, so the topic of this video is conjugate acid and base pairs. So basically from this lesson, what you need to be able to do is identify the conjugate acid and the conjugate base when you're given a neutralization reaction, or the reaction of an acid with a base. But the important thing is that these are mainly identified when we're using Bronsted acids and bases, okay? So not our typical arrhenius acid that contain H or our bases that contain OH. These, remember, are the alternate definition for an acid and a base, which we'll review here. So remember, a Bronsted acid is something that donates or gives off an H+, and then a Bronsted base is something that accepts H+, because again, typically the base is something that gives off OH, but Bronsted bases don't contain an OH to give off, so instead they'll do the opposite of what the acid does and accept the hydrogen ion. So the new definitions that we're going to learn then today for conjugate acid and conjugate base. So basically what the conjugate acid is just whatever the base turns into after it accepts that H+, right? So starting on the left-hand side, your base will have one less hydrogen compared to the right-hand side, the product side, where it shows that it gains a hydrogen. Okay, so that would be your conjugate acid, is what the base turns into after it accepts H+. So for example, if the base was H2O, then your conjugate acid becomes H3O, right? Because this is showing that we're starting as a base because it was H2O, now becomes H3O, showing again that it gained or accepted a hydrogen. Okay, so that's how these would be labeled, as this is our base, and then this H3O is the conjugate acid. Okay, so that's why this blue arrow here shows that these two go together. So the left-hand side, your base, always gets paired on the right-hand side with its conjugate acid. And then vice versa, your acid will pair with the conjugate base, and all that is what the acid turns into after giving off its H+. Okay, so again, just the opposite of the conjugate acid. So starting with your regular acid on the left-hand side, it will donate or give off an H+, and then have one less on the right-hand side. So an example of that, again, if we're still using water, remember, water is amphoteric, meaning it can act as an acid or a base, so we can use that same compound here. So if we have water now acting as an acid, remember it gives off or loses an H. So over on the other side, the conjugate base, right, that's what pairs with the acid, so now we're following the red arrows, is on the other side. Okay, so basically just these two terms that work together is your acid turns into the conjugate base, and then your base turns into a conjugate acid. So how we have to do this, again, is being able to actually identify them when you're given a reaction. So we're going to go through a couple examples together and see how you do this. So if this is our first reaction, we have HCl reacting with NH3 to form NH4+ and Cl-. So basically with your reactants that you're given on the left-hand side, you want to follow it on the product side and basically see wherever that matching ion is, right? So since this contains the chlorine, that's going to be what it turns into on the other side. So that's what you first have to know, and then you can start figuring out whether it's the acid or the base, depending on whether it gains hydrogen or loses hydrogen. So again, over here, it starts as HCl and then becomes just Cl-. So in that case, it lost a hydrogen. So that means if it's, again, donating or giving off hydrogen, that's your acid. And then whatever substance it pairs with, again, wherever that common ion is, now it has one less. So this becomes our conjugate base. And why basically we call it this is because if we read this in reverse, so if we were going this way, it's now acting as a base, because if it turned back into HCl, it would have to accept that hydrogen, which is what a base does. Okay, so then obviously our other substance here must be the base, but just to double check, bases, remember, accept or gain a hydrogen. So here we see NH3 turns into NH4, so it did gain hydrogen. Okay, so then that means that this was our base. And remember, the base pairs with your conjugate acid, which again, read it in reverse. Acids will lose, so convert it back, and it loses that hydrogen on the other side. So let's try another example. If here we have NH4+ reacting with H2O, turns into NH3 and H3O. Okay, so we can see the common substances that go together, the NH4 and the NH3 versus H2O and H3O. So here, NH4 turns into NH3, meaning that it lost a hydrogen. So when something, again, donates or loses hydrogen, that is your acid. And then the acid, whatever it turns into, always pairs with your conjugate base. And then vice versa. So now we have H2O must be our base, because again, bases accept hydrogen, so which we see on the other side, it's listed as H3O. So 3 is 1 more than 2. So again, that is our base, which pairs with your conjugate acid. Okay, so it's basically opposites. Whatever your acid is, the substance that it has in common or that it kind of pairs with on the other side is its conjugate base. And then whatever base you start with, it pairs with its conjugate acid. So one last example, I'll try and have you guys kind of pick these out as well. So here we have HCO3 minus plus HCl turns into H2CO3 plus just Cl minus. Okay, so again, look for that common ion. So here I see CO3 and CO3. So those are the two substances that we're going to be comparing. And then again, HCl versus just Cl. So here, HCO3 turns into H2CO3. So think, did it gain a hydrogen or lose a hydrogen? And it gained, right? It went from 1 to 2. So if it's gaining hydrogen, this is our base. And then just remember, bases always pair with the conjugate acid. And then HCl, if it's an acid, it must give off H, which we see, it turns into just Cl minus on the other side. So that means that HCl is our acid. Oops. And then Cl minus would just be our conjugate base.